Today in the workshop, we're learning to use the Raspberry Pi GPIO. We'll see how the GPIO works and how to easily control devices attached to it using Python and the gpiozero library. We're cooking up something special today, so welcome to the workshop. Hello and welcome to the workshop, and today we are going to be working with the Raspberry Pi GPIO, the General Purpose Input-Output Bus. That's the 40-pin connector that you're going to see on all modern Raspberry Pis, as well as a number of other single-board computers, because this GPIO has been unofficially adapted as a standard among many single-board computer manufacturers. Now here in the DroneBot workshop, when we get sensors or motors or displays, we tend to use an Arduino to control them, and there are a lot of good reasons for that. Arduinos are relatively inexpensive, they're fairly easy to work with, there are a variety of libraries supporting all sorts of I/O devices, and of course they've got all those wonderful little I/O pins. But sometimes the Arduino doesn't have enough computational power. After all, the Arduino really has about the computational power of some of the processors we were working with in the late 1970s. And sometimes your project needs a bit more intelligence, and that's when you can turn to something like a Raspberry Pi or other single-board computer. So before we start working with the GPIO, I wanted to see how the Raspberry Pi and the Arduino stacked up against each other. So let's compare the Raspberry Pi to the Arduino. The Raspberry Pi is a microcomputer. The Arduino is a microcontroller. This is the most significant difference between the two platforms. The Raspberry Pi uses an operating system on a micro SD card. The Arduino uses a bootloader contained on the MCU chip. The Raspberry Pi has USB, video, camera, display, and audio connections. The Arduino has a USB connection. The Raspberry Pi has I2C and SPI buses. The Arduino also has I2C and SPI buses. The Raspberry Pi has a number of digital I/O ports. The Arduino has both digital I/O ports and analog input ports. The Raspberry Pi runs on 5-volt USB power. Most Arduinos run on 5-volt USB, as well as a second power connector that can accept 8 to 20 DC volts. The Raspberry Pi is a commercially patented product. The Arduino is an open source design. Some models of the Raspberry Pi use up to a 1.5 GHz 64-bit quad-core CPU. The Arduino AVR-based microcontrollers use a 16 MHz 8-bit single-core microcontroller unit. Raspberry Pis have from 512 MB to 4 GB of RAM. Arduinos have from 2 KB to 8 KB of static RAM. The Raspberry Pi has 26 digital I/O ports. The Arduinos have 14 to 54 digital I/O pins, depending upon which model you're using. The Raspberry Pi has no analog inputs. The Arduino has 6 to 16 analog inputs, again depending upon which model you're using. Some models of the Raspberry Pi have integrated Bluetooth and Wi-Fi. The Arduino boards do not have Bluetooth or Wi-Fi. Some Raspberry Pis have an Ethernet connector. The Arduinos do not have a built-in Ethernet connector. You can expand the functionality of your Raspberry Pi by using HATs, hardware attached on top boards. The Arduino has a similar expansion capability using shields. When you get either board, you'll need a few other things to get it to work. With a Raspberry Pi, you'll need a micro SD card, a USB or USB-C power supply, depending upon which board you've got, a keyboard, a mouse, an HDMI monitor, and a number of adapter cables as required for your own setup. To run the Arduino, you will need a USB cable and a computer. So which of the two will you be using for your next project? So now that we've seen the difference between the two different platforms, which one makes the most sense for your project? Well, if your project requires some very precision timing, or if you need to measure pulse widths to a very high degree of accuracy and they're relatively low frequency, then the Arduino probably wins out. Microcontrollers are generally better at doing things like that than a microcomputer. However, if you need to add a lot of intelligence to your project or interface it to the internet, then something like a Raspberry Pi or another microcomputer would make a lot more sense. Sometimes the choice isn't that easy. Let's say, for example, you were designing a controller for your sprinkler system and you had a number of devices you needed to control. Well, both of these devices, the Arduino and the Raspberry Pi, could be good choices for a design like that. And if you wanted to add a few sensors for things like soil moisture or to find out if it was raining right now, you could add that to both of the platforms as well. But if you wanted to add something more advanced, like let's say the ability to connect to weather forecasts and find out if it's about to rain so that you didn't water your lawn an hour before a huge rainstorm, then something like a Raspberry Pi makes more sense. So if you decided to use a Raspberry Pi, which Pi should you use? There are a variety of them to choose from. So let's go and take a look at a few of those Pis right now. Alright, ladies and gentlemen, welcome to the party that we're having with some of the Raspberry Pis that live here in the DroneBot workshop. And since some of these boards haven't been out of their anti-static bags for a while, I thought I'd give them each name tag so they could all introduce themselves to each other and mingle a little bit. So let's get introduced to a few of these boards. Now this is the Raspberry Pi 2B. This board is a few years old, about maybe 4 years old right now, maybe close to 5 years. Essentially, it's still a very valid Raspberry Pi. It's got all of the standard connectors. There's a camera connector over here. There's a display connector here. This, of course, is the 40-pin GPIO that we're going to be working with today. It's got a connector for HDMI over here. This is a micro USB connector that you use for a power supply to power it. Now, on this side, we've got an Ethernet connection. I believe this was only 100 megabit Ethernet, and some USB 2 connections, 4 of them. Now this board doesn't have any integrated Wi-Fi or Bluetooth on it. And next to that, we'll put your name tag back on so we know who you are. This is the Raspberry Pi 3B Plus, and it's looks a lot like the other board. It's got the same connectors on it. However, this board also has Bluetooth and Wi-Fi on it, and so it's also got a faster Ethernet. I believe it goes to 300 megabits. It isn't full gigabit, but it is faster than the 100 megabit Ethernet that the 2B had on it. Then we move up to these three, and now these are the latest members of the Raspberry Pi family, the Pi 4B. And the only difference between them is the amount of RAM they have. This one has 1 gigabyte, this has 2 gigabytes, and this has 4. Otherwise, they look the same. They look a bit different than the other boards do in terms of connectors. They got the same GPIO connection and the same audio connection, the same camera and display connections, but it uses a USB-C for the power, and it uses 2 micro HDMI outputs here because this can handle 2 4K video outputs. These are 1080, these ones here. And so it uses these micro HDMI connectors. It also has on the USB, 2 of the ports are USB 3 now, and this is a full gigabit Ethernet, and of course it also has Wi-Fi. And as I said, this one comes with 3 different amounts of memory. Now on the other end of the scale, we have the Raspberry Pi Zero. This is the amazing little $5 computer, quote unquote. And as you can see, it's pretty basic. It has a GPIO that we're going to be working with today, but it doesn't come with a connector soldered on, although there is one version called the 0WH, and WH literally means wireless, and a header that does have the connector on it. Otherwise, you can solder one on yourself or just solder to the individual pins that you need. So it's kind of versatile. As you can see, it's very small. It's got a mini HDMI connector, so not to be confused with the micro connector this one is using. It's a mini HDMI output. It's got two micro USB jacks. One of these is for power and the other one is a USB connection. It's your only connection into the board, and it's got a camera connection. Now it's got the 0 and the 0W, and the big difference is the 0W costs twice as much. This is a $10 computer, but for the extra $5 you get integrated Bluetooth and Wi-Fi, so it's a more useful one, and it is actually the model that we're going to be working with today. And so there you have it, some members of the Raspberry Pi family having a little get-together. Now, any of the Raspberry Pi family members that we just looked at would be just perfect for our experiments today. What I'm going to be using is the Pi Zero W, and the reason I chose it over the Pi Zero was because of its integrated Wi-Fi and Bluetooth, and specifically the Wi-Fi. Now, I won't be using this today, but in future experiments I'll want to download additional libraries, and it'll be a lot easier to do that on a machine that is connected to Wi-Fi than one that isn't. But of course, you don't just use a Raspberry Pi Zero or Zero W. You need a few accessories to go along with it in order to do the experiments. And you certainly don't need everything I've got shown here, so don't panic. But I want to show you a few of the things that you will need in order to work with the Raspberry Pi Zero or Zero W. Now, first of all, let's take a look at the Zero W over here. As you can see, it's a very tiny computer, and this is the connector over here for the micro SD card, and so you're going to need a micro SD card. So I've got one over here that I can use. You're going to want to get a good quality micro SD card as well. Don't buy just a store brand or something. Buy a name brand micro SD card that has very high specs. On the side here you can see that we've got a connection for the HDMI, but this probably doesn't mate with the HDMI cables you have. So in order to resolve that, I've got this little adapter, and this little adapter just plugs into the HDMI and lets you put a full-sized HDMI into the device. Now, there are two micro USB connectors over here. This one is for power, and this one is basically a micro USB connector. Now, since you're going to have to connect a keyboard and a mouse, you're going to need to find a way of doing that, and one way of doing that is with one of these little hubs, and these are really neat. These actually not only have 3 USB outputs, full-sized USB, but they also have an Ethernet connection. So this would be good for the Pi Zero as well. So basically you can add that onto your Pi by plugging that in over here. Now you've given it a few extra USB ports that you'll need. And of course you're going to need a power supply. Now I've got a few supplies back over here. This is a really good power supply for the Raspberry Pi Zero. It's a 2.5 amp USB supply, and that's about the minimum current you'll want. For the other Pis, you'll probably want a 3 or a 3.5 amp if you can find it. What I like about this supply is it has an on-off switch over here, and that's one thing that all of the Pis are lacking. Now, I just brought this one out as well. If you're working with a Pi 4 and not one of these, you're going to need a USB-C supply, and this is the official Raspberry Pi USB-C power supply for that device. Now, of course, the Pi Zeros that you've seen over here are lacking one thing. We're going to be working with the GPIO, but right now there is no connector on there. Well, you can solder a connector on. I've done that with this Raspberry Pi Zero W, and this is the one we're going to be using today. And then after that, you can connect to this GPIO. Now, there's several different ways you can do that. One of the most common ways is to use one of these devices. It's sometimes called a T-cobbler, although I think that's a brand name. It's basically a T connector, and it's got a 40-pin adapter over here, and these pins over here can be inserted into a solderless breadboard. You'll see that they've already got markings on this so you know what pin you're connecting to. And then you just use this ribbon cable to connect to here, and then connect the other end up to the GPIO onto your Raspberry Pi. And that makes it very easy to get at all the GPIO pins. If you don't want to do anything so esoteric, though, these things are great. These are just male to female DuPont connectors, and you can rip them off like I've done to a couple over here, and you can just use the female ends over here to connect to the specific pins on the GPIO that you're using, which is pretty well what I'm going to be doing today, because I'm not going to be using a lot of the pins today. There's a few other things I have on the desk over here that would just make your life easier when you're prototyping with this stuff. These are little cards you can use to make what they call P-hats, which are small hardware attached on top boards that'll attach to the top of your Raspberry Pi Zero. And you can use things like this in order to connect them. So you can use this for prototyping. And this is a little adapter that you can use to go onto the top of here, still allow you to attach a hat, and yet attach a cable as well, so that you can use the T device over here. So there's a lot of ways that you can prototype with the Raspberry Pi Zero. So now that we've taken a look at this, let's start working with our GPIO. So let's get familiar with the Raspberry Pi General Purpose Input-Output, or GPIO bus. The 40-pin GPIO bus is on every modern Raspberry Pi. This is a Raspberry Pi Zero where there is no connector soldered in. Other models have a connector here. You'll notice pin 1 is identified because it is marked as a square as opposed to a circle, and that all of the even pins of the bus are on one side and the odd pins on the other side. Several of the pins are designated as GPIO pins. These pins allow digital input and output to the Raspberry Pi, and they operate on a 3.3 volt logic level. 2 of the pins provide a 5 volt output. There are also a number of ground pins on the GPIO bus. There are a couple of pins that provide a 3.3 volt output. And finally 2 pins for the IDE EEPROMs that are used on the Raspberry Pi hats, which attach to the connector. Earlier models of the Raspberry Pi used a 26-pin GPIO, and the first 26 pins of the modern 40-pin one are identical. Some of the GPIO pins have particular significance. Pins 3 and 5 are the I2C connections. Pins 8 and 10 provide serial I/O. And pins 19, 21, 23, 24, and 26 are the SPI connection. GPIO pins can be referenced using multiple naming schemes. The most common one is the Broadcom pin number scheme. This is the actual pin number on the Broadcom chip and not the pin number on the GPIO. The physical pin number is also sometimes used. With many GPIO libraries, you need to declare which numbering scheme you are using at the beginning of your program. Note that the logic pins on the Raspberry Pi are 3.3 volt and not 5 volt. These pins are not 5 volt tolerant, and applying 5 volts to them could destroy your Raspberry Pi. The power pins can supply the hats and other attached devices as long as they don't consume a lot of current. The 5 volt pin can also be used to power the Raspberry Pi, but this is not advised, as an internal fusible link will be bypassed if you power the board this way. Now, when we're working with the Raspberry Pi, we're going to be coding in Python, and we're going to need to use a library to work with our GPIO. There are several choices of libraries or APIs that you can install into Python to work with the Raspberry Pi GPIO. One of the original ones was called Wiring Pi, and it was pretty well superseded by the RPI GPIO, and you'll probably see more examples for the RPI GPIO than anything else. There is also another one called Pi GPIO, and that has an advantage in that the code in that is pretty well transportable to just about any other single board computer as well. I understand there's even a Windows implementation of that. But the one that we're going to use today, the library that we will be using, is one called gpiozero. This is a library that was written by and endorsed by the Raspberry Pi organization, and it is a good library for beginners with the GPIO because it actually acts like a bit of a shell, and it insulates you from a lot of the fine points that you need to work with on the GPIO. For example, when you're using an input, it will automatically invoke the built-in pull-up resistors in the Pi so that you don't have to do any extra coding for that. So you'll find it really easy to work with. And it comes with a very excellent set of examples as well. And so we're going to follow through a few of those examples today when we work with our Raspberry Pi GPIO. And so the best way to learn about working with the gpiozero library is to read the documentation, and you'll find a link to that documentation in the article that accompanies this video. Now we're going to go through a few of the basic recipes that they have, and these are basically just examples that use a simple LED and push button switch, and we'll go through a few of them, and for every one of these examples they supply the Python code, and for most of the examples they show you more than one way of accomplishing everything, and so that's an interesting thing to look at as well. And I'd urge you to go through some of the other examples as well, even the ones we're not going to be using. They do things like eventually attach things like motion sensors, light sensors, distance sensors, and even motors up to the Raspberry Pi and control it through this library and through the GPIO. Once you've done that, you can go into some more advanced examples down over here, as well as remote GPIO examples, and migrating from the rpi.gpio library to this GPIO library. So to learn about the gpiozero library, this is probably the very best result, and we're going to go through a few of these examples today. And so now that we know which library we're going to be using and we've got everything ready, it's time to hook it all up. So let's go and take a look at the wiring diagram in which we'll hook up both an LED and a push button switch to our GPIO. Now for our GPIO experiments, we of course are going to require a Raspberry Pi. I'm going to be using a Raspberry Pi 0W, but any modern Raspberry Pi with a 40-pin GPIO will work. Note that the 0 and the 0W do not have a header installed on them. The one that I'm going to be using will have a header soldered on. You'll also need to configure your Raspberry Pi with the latest version of Raspbian, and I'm going to assume that you've got a mouse, a keyboard, and a video monitor connected to the device. In addition to the Raspberry Pi, we're going to need a momentary contact push button switch, an LED, I'm showing a red one, but any color will work, and a dropping resistor for that LED, and I'm using 220 ohms. Pin 6 on the connector is one of the many ground connections, and we're going to connect that to the cathode of our LED. Pin 11 is also referred to as GPIO pin 17. We'll connect that to one side of the dropping resistor, and the other side of the dropping resistor will connect to the anode of the LED. Pin 3 will connect to one side of the push button switch. This is also known as GPIO pin 2. We'll connect the other side of the switch to ground. And this completes the wiring for our experiments. So here we are at the Raspbian desktop. Now, if this is a brand new Raspberry Pi and you've just installed Raspbian, the first time you log in, you'll get walked through a series of steps that ask you questions about the type of keyboard you have and the locale that you're in and your language, etc. You'll need to answer those questions. Another thing you might want to do is set up the Wi-Fi networking so that you have networking ability. Now, we don't need that for any of our experiments, but it might be handy for you to be able to open, say, a web browser to reference the gpiozero library documentation, or perhaps the article accompanying this video. Now, one thing you will need to set up on the Raspberry Pi is you'll need to enable the camera interface, because we'll be using the Raspberry Pi camera. And so go down to Preferences, and then go to Raspberry Pi Configuration, and then go to Interfaces. Now they have a number of interfaces here, and by default they're all going to be disabled. You'll notice my camera, which is the very first one here, is enabled, and I've clicked that. Go and click yours and enable it, and then click OK. Now when you do that, you'll need to reboot the Raspberry Pi before you can continue. Now what we are going to be doing today is we're going to be doing our GPIO experiments with the gpiozero library, And I've got the documentation for that up over here. Now you could go through the examples and just copy the examples and paste them into your Thonny IDE, which is the IDE we'll be using to work with Python on the Raspberry Pi. But what I've done is I've created a number of individual Python files, these ones over here, and these have each of the individual examples on them, and I can just right-click them and open the Thonny IDE. Now if you'd like a copy of all these individual files, I have them available in a zip file, and you'll find information about getting that on the article on the dronebotworkshop.com website. So once you get yourself set up, we're ready to work with the Raspberry Pi GPIO. Now, anyone who has ever worked with an Arduino is familiar with the blink sketch. It is sort of the hello world sketch of the Arduino world, in which it just blinks an LED on and off, and they even use the LED attached to pin 13 so that you don't need to hook anything to the board because there's an internal LED attached to that pin. Well, the first couple of programs that we're going to be running today in order to work with the Raspberry Pi GPIO and the LED perform the exact same function as the blink sketch. They'll flash the LED on and off. And I thought it would be a good idea to compare the programs we're going to be using in Python with the Arduino blink sketch. This will be especially useful, I think, for those of you who don't work with Python or haven't worked with it very much, because you can compare the coding structure between the C++ used in the Arduino and the Python that we're going to be using with the Raspberry Pi. And I'll leave it to you to decide which is an easier way to flash an LED. And here we have the classic Arduino blink sketch. And of course, this is probably the first sketch that you used when you first got an Arduino. And many Arduinos come with this sketch already running on it, just as some sort of a quality control test. Now, let's just take a look at how the sketch works. We're using an LED called LED built-in, and this constant refers to the LED that's already wired onto the Arduino board, so you don't actually need any extra hardware to run this sketch. Now, the built-in LED is also connected to pin 13, and you can connect an LED to pin 13 for this as well if you wish. So in the setup, we define the LED built-in as an output, and then we go into the loop. And on the loop, we simply write the LED high, which turns it on. We delay for 1,000, that's 1,000 milliseconds, which is a second. And then we write it low, which turns it off, and we delay for another second. And if we take a look at our LED, I've already uploaded the sketch, you can see that indeed it is flashing once a second. Now, if we wanted to modify this, we can modify the delay period. So if I, for example, made the delay 2,000 instead of 1,000, the LED should stay off and on for twice as long, so it will blink slower. Now I'll send that up to my Arduino. And as you can see, it had the effect that we thought that it would have. Now, of course, what we're doing is we're creating a square wave and we're sending it out to the LED. And by manipulating these delay times, we can change the duty cycle of the square wave. So if we wanted to, for example, we could keep the LED and set that to 500. That'll be on for 2 seconds and off for half a second. And there you go. And so quite simple, but I want you to bear the principles of this sketch in mind as we then go and look at the Python code we'll be using on the Raspberry Pi to accomplish the same thing. So here's our Raspberry Pi, and as you can see, I've got it doing the same thing we had our Arduino doing. It's blinking the LED. Now you can see my hookup over here, very simple. I've got my LED dropping resistor and push button on this small solderless breadboard. This orange wire comes from the push button. It goes to physical pin number 3, which is GPIO 2. The yellow wire is from the dropping resistor that goes to the LED, and that goes to pin number 11, which is GPIO 17, and then the black wire is just a ground connected to pin 6. And my LED is flashing away. Let's see how that actually works. Now here's the Python code that we're looking at in the Thonny IDE, which is an IDE you can use for working with Python on the Raspberry Pi. There are other IDEs as well, but this is the one that it defaults to now. Now, if you look at our Python code, you can see a lot of similarities to the C++ code we looked at in the Arduino sketch. Now, we do need some libraries over here, which we didn't need in the sketch. We'll start off in the gpiozero library. We're going to import a class called LED, which, as its name implies, is a class that has a number of functions that lets us work with LEDs. We'll also, from the time library, import a class called sleep. And sleep is very much like the delay function in the Arduino C++ code. It just makes the code stop for a predetermined amount of time. Now we'll define an object to represent our LED. We're going to call it red, and we'll use the LED class and point it to GPIO pin number 17, which is where we have our LED connected. And then this is a loop. The while true is always going to evaluate as true, and so it is going to run the 4 statements below. Now remember, in Python we don't use brackets. Instead, we nest things by using indents. So these 4 things will run right after each other. And so we'll take our red LED object and turn it on. Then we will go to sleep for 1 second. This parameter represents seconds. Then we'll turn it off and we'll go to sleep for a second and repeat. And as you saw, that makes the LED flash back and forth, once on and once off. And that's pretty cool. The same thing that we did with the Arduino sketch we can do with this Python program. If I wanted to make this LED flash slower, I could change these values to 2, thus giving it 2 seconds. You could also use fractions, by the way, so things like 0.5 of a second are valid values. And we'll send that up to the LED. Now let's just stop it and start it again. And as you can see, our LED is flashing a lot slower than it was before, because now it's on for 2 seconds and off for 2 seconds. And so basically we've used a similar piece of code to blink the LED. There's another way we could do it as well that they show you in the gpiozero examples. It's the next example, actually. If you take a look at the code for this, this is even simpler. Again, we import the LED object, and we now import from a signal library something called pause, and we'll once again define red as being the object representing our LED. Notice there are no semicolons at the end of the statements in Python. And then we'll just simply use the blink function of the LED class and say red blink. And so we'll just tell it to go off and blink. And there you see it blinking, and it's back to blinking it once per second. Now, there are parameters you can give this. You can give it the on time and the off time. Let's make it blink faster this time. Let's give it an on time of 0.5 and off time of 0.5 as well. And there are additional parameters as well here. You can do a fade in and a fade out to the LED as well. And so let's stop our code. And I'm using my keyboard right now to do that, by the way, with the F5 key. And there you can see our LED is blinking a lot faster now because we've given it those parameters. And so this is an even simpler way of blinking an LED using Python. So as you've seen, using the gpiozero library with Python makes it very simple to flash an LED because it has a class exclusively dedicated to working with LEDs. In fact, I think it makes it a bit easier than the coding on an Arduino to do the same thing, but that's my own personal opinion. Now, in addition to classes for the LED, it also has a class for working with buttons, which we can use with our push button. So let's go take a look at a few other coding examples now. Now, before we move on to the push button, let's do a couple of other things with the LED involving pulse width modulation. Now, PWM, as you know, is a way that we can vary the brightness of an LED or control the speed of a motor, and you can do that with the Arduino on certain digital I/O pins. You can do it with the Raspberry Pi as well. And we're using a class called PWM LED from the gpiozero library to regulate the brightness of the LED using pulse pulse width modulation. We're also importing the sleep class again like we did in our original program. We'll define our LED as being PWM LED on GPIO pin number 17, and then we go through a while true loop again. We'll set the value parameter of the LED to 0, which will turn it off. We'll go to sleep for a second, then we'll set the value to 0.5, which brings it to half brightness, sleep again for a second, and then we'll go and set the value to 1, which turns the LED completely on, and we'll keep it on again for 1 second and then repeat. And so if we look at our LED, we can see it's going to half brightness, now full, now off, half, full, and off, etc. And of course we could adjust the number on the sleep parameter to keep it on those different stages for different amounts of time. Now there is another function that PWM LED has that is interesting, that's similar to this, and it is the pulse function. So here is a program that uses the pulse function, and LED pulse, let's just go and send that up to our board. I'm using my F5 key again. And there's an LED pulse. Now as you can see, it's got kind of a fade in and a fade out. And pulse has several parameters that you can adjust to adjust the rate of this and the amount of time for the fade in and the fade out as well. And that's all in the gpiozero documentation, to which you'll find a link, of course, in the article accompanying this video on the dronebotworkshop.com website. Okay, so one final thing that we can do with the LED is start working with our push button. Now here we have the first piece of code that we're going to use to work with the push button. And we're going to import two classes from gpiozero, and this is how you import multiple classes. You just separate them with a comma. We're going to import the LED class and the button class, which allows us to work with push buttons. And again, we're going to put a pause at the very end of the program. If the program does come to an end, we will pause it. Now we once again define the LED as a LED object on GPIO pin 17, and button will be a button object. This is our push button on GPIO pin number 2, which is physical pin number 3. And so when the button is pressed, when we get a when pressed event, we'll turn the LED to on, and when the button is released, we'll turn the LED off. And that seems pretty basic, and let's take a look at it. And yes, indeed, when I press a button, I can turn my LED on. Now, of course, this is not a particularly useful little program, since we could simply do this without the Raspberry Pi and just give ourselves a bit of voltage and turn the LED on directly from the button. But the point here naturally is to learn how to use the Python code. We're getting an input from the button and sending an output to the LED. Now, the other way of doing this is with this example. And with this example, we're importing the same two things, the LED and the button classes, and we're going to use pause again at the end of the program. We're defining the LED and the button as the same, but we're simply saying LED source equals button. And so this is a much faster way of accomplishing exactly the same thing. So as you can see with the gpiozero library, your coding in Python is actually pretty minimal. Now let's look at a few other things we can do with the button. Now this is a program that basically uses the wait for press event from the button. So the button is actually going to sit here and not do anything. This code won't do anything until the button is actually pressed. And so let's send that up to our... And there, as you can see in the bottom here, which is the shell, I just pressed my button and it said the button was pressed. And now the program is over. Pressing the button further won't do anything for me. Let's take a look at another program that'll show us when buttons are pressed and released. Now here's another one. We're going to import button, and we're going to use the pause. And we're going to define two functions. One of them says say hello, and we're going to print hello. And the other one says say goodbye, and we're going to print goodbye. And everything we print is going to end up in the shell down here, by the way. Now, when the button is pressed, button when pressed, we take the say hello function, so we should print out hello. And when the button is released, we should say goodbye. And this should continue to work continuously. So here I hold it down, release it, and I've got hello and goodbye. Now I want to show you one other thing that's rather interesting and will illustrate one of the differences between running code on the Raspberry Pi than running it on the Arduino. Let's go and take a look at the very simple button example. And basically when it's true, if the button is pressed, it says the button is pressed. If the button is not pressed, it says it isn't pressed. Now what I'm going to do over here is I'm going to run this code, but I'm going to run this code in the terminal. This will open up my terminal, and the button is not pressed, button is pressed, I'm holding it. What I want you to notice though is that I'm also getting results in the shell for the previous program. In other words, both of these programs are running simultaneously. And I think that's pretty cool that you can actually run two things at the same time. Of course, you got to be very careful doing that, but that just illustrates a bit of the power you have using the GPIO with the Raspberry Pi. Now, as we saw earlier when we compared the Arduino and Raspberry Pi, the Raspberry Pi has a number of other I/O interfaces that the Arduino does not have, and one of them is a CSI connector for a small camera. And for our last experiment, we're going to connect a Raspberry Pi camera up to that CSI interface and use a couple of push buttons attached to the GPIO to control it. For this experiment, we'll need our Raspberry Pi again. And we'll also need a Raspberry Pi compatible camera. Any type will suffice. We'll need two momentary contact push button switches, which we'll call SW1 and SW2. We'll begin by connecting our camera to the camera connector on the Raspberry Pi. Make certain that you use the correct cable for this, and note that the Raspberry Pi 0 and 0W have a smaller camera connector than the other models do. We'll begin our wiring by connecting pin 6, which is a ground, to one side of each of the push-button switches. We'll then connect pin 3, which is also GPIO pin 2, to the remaining side of SW1. And finally, we'll connect pin 5, which is GPIO pin 3, to the other side of SW2. And this completes our wiring. So here's our camera test setup. I've got my two push buttons over here. The red one on this side is SW1 and the one on this side is SW2. SW1 being connected to pin 3, which is GPIO2, and SW2 is connected to pin 5, which is GPIO3. Now up over here you can see I've got the camera suspended and it's facing down toward the Raspberry Pi, so this way our Raspberry Pi can take a selfie. Now let's look at the code we'll need to achieve this. This is the code that's been provided, and we'll start off again by importing a number of classes from libraries for the button, for the camera. Also, we want date, time, and a pause. Now we're going to define a couple of objects to represent the push button. We're only using one button in this case, the red one, and we'll also define an object for the camera. Then we start by defining a function that we're going to call capture. And in capture, we take the date time of now, which is the immediate date time in ISO format, and assign that to a variable called timestamp. And then we use the camera object and we do a capture, in other words, take a picture, and we're going to send that capture over here to the root of our Pi directory, and we're going to use the timestamp itself as the name of the file .jpeg. So we're going to take a picture with the timestamp being the name of the file. And then we go out of this function here and take a look at the actual program. And so we're looking for a when pressed event from the button. When that happens, we'll execute the capture function and take our picture. And then we'll start everything over again. So let's go take a look right now in the root of the Pi directory. And we'll press the button. And it appears that we have created a file. And we'll just go in and open that file. And there we have a selfie of the Pi 0 and a little bit of my thumb in there as well. So it does appear to work, and it's still running. Every time that I press the button, as you can see, it'll take another picture. So this is a great way to take a selfie of your Raspberry Pi. Now here's another program to control our camera. This time we're going to be using both push buttons. One button will provide a preview function and the other button will take the actual picture. Now we start off by importing the same libraries and classes from those libraries, and then we define our two buttons. We could define left button as being the one attached to GPIO 2 and right button as the one attached to GPIO 3. So left button in my case is the one indeed on the left, which is the red push button. And this is the one that's going to be providing the preview function. The right button will take the picture. And then we also define an object, of course, for the Pi camera. The function capture is identical to the one we used last time. It'll take a picture and label it with the timestamp of the current time. Now here's where we define how the buttons work. The left button is the preview one, and so when it is pressed down, we do a start preview, and as long as that button is held down, the preview will continue. And then when the button is released, it'll stop the preview. The right button, when it is pressed, just executes the capture function as before. So let's go into our directory again, which I've cleared out of files. And I'm going to hold down the preview button. And as you can see, I'm getting a preview. And so I can move around and try to get the ultimate picture right now for my selfie. And now I'm going to press the other button. And we did indeed get a file, which we can open. And naturally, it's going to be a picture of what we just looked at. And there you go. And again, my thumb got in the picture. And you can also do them simultaneously. I can hold the preview down, move the camera around, try not to get the thumb in there, and at the same time do a quick press of the button and make another picture at the same time. So essentially, with a few lines of Python code, we've built ourselves a camera, which is pretty impressive. And so today we've learned the basics of working with the Raspberry Pi GPIO, and we've seen how libraries like gpiozero can make it very easy to work with things like push buttons and LEDs. And in future videos, I'm going to be showing you how we can do additional things with the GPIO. There is a lot to it, and we can hook up all of the same sensors and display devices that we've used with the Arduino. We can control motors with it, and of course there's the SPI and the I2C bus on there. So you'll be seeing a number of additional videos about working with the GPIO in the near future. Now the best way to find out about those videos is to subscribe to the channel. And when you subscribe, please click on that bell notification button, and that way you'll be notified every time I create a new video. Now if you'd like to get the code that I used in today's video and some easy to use Python files instead of copying them off of the gpiozero website, or if you need a bit more information about what we talked about, you'll find an article that accompanies this video, and the link to that article on the dronebotworkshop.com website is below the video. You'll also find the link below the video to join the newsletter. The newsletter is my way of keeping in touch with you. Every 2 weeks I send out a newsletter just to let you know what's going on here in the workshop. And finally, if you want to discuss today's video, or if you'd like to make suggestions for new content for the DroneBot Workshop YouTube channel and website, then go over to the DroneBot Workshop forum. You'll also find the link to that under the video, and you can discuss the topic with fellow enthusiasts just like yourself. So until we meet the next time, please take good care of yourselves, and I hope to see you again very soon here in the workshop. Goodbye for now. Well, I don't know how it happened, but it appears we had a gate crasher at our party. This guy came in masqueraded as a 3B+, but it turns out he's only a 3B. And this fellow over here, we'll get rid of this guy. This guy is really the 3B+, and as you can see, he's got a shiny silver chip because he's faster. He's also got a power over Ethernet connector over here. So this is his name tag, and we'll have the contact security about that guy over there.